Consider the polynomials with degree less than n. We want to define an inner product on this. We've established that Pn is isomorphic to Rn plus 1. So in theory, we could extend the dot product in Rn plus 1 to Pn just using a basis transformation. But this turns out to be bad. In particular, the inner product tells us the length of a vector, and we don't want the length to depend on how the vector is written, i.e. we want the length to be independent of the basis. It turns out the inner product of two vectors, f and g and Pn, is the integral from 0 to 1 of f of x times g of x. This is the extension of the dot product. Just compare them. In the dot product, you add up taking the product of the matching coordinates. And that's kind of exactly what you're doing here. Let's check if the standard basis of P2 is orthonormal. All we need to do is take all the inner products. First, check the inner product of 1 with itself. We want this to be 1, which it is. Cool. Second, the inner product of x with itself. We want this to be 1, and it's not. We could stop the example here because the answer is no. This is not an orthonormal basis. We'll keep going because why not? X squared with itself comes out to be 1/5. We would hope that the inner product of 1 and x is 0, but it's not. 1 and x squared is also not 0. X and x squared? Of course not. So this kind of sucks. Our standard basis not being orthonormal means we can't easily determine coordinates of functions. At the moment, this isn't a big deal since obviously we can just see the coordinates. But what if we weren't dealing with polynomials? What if our function was more complicated? How do we easily find coordinates then? How do we fix this? Clearly, the answer is to find an orthonormal basis. We'll make the set 1, x be orthonormal. 1 is already a normal vector, which is good so we don't need to change it. X, however, is an issue. It's neither normal nor orthogonal to 1. Here's an idea of what we need to do. We have a vector u and a vector v. We want to replace v with a vector perpendicular to u. But we already know how to compute this. Projections. Find the projection of x onto 1. The projection formula doesn't change at all, and this is 1/2. That means the orthogonal projection of x onto 1 is x minus 1/2. Of course, this needs to be a normal vector, so let's find the length. This will involve a tiny amount of calculus and a touch of algebra, but it turns out the inner product is 1/12. Hi everybody. See that square? Yeah, that's supposed to be a cube. That means all the 12s are supposed to be 24s. I screwed this up. I could have gone back and re-recorded the audio and fixed the video. But all the concepts are right, and it would have taken me a lot of work, so I didn't. Therefore, the set 1, square root 12 times x minus 1/2 is orthonormal. Why the square root of 12, you may be wondering? Well, the length of a vector is the square root of the inner product, so the length of x minus 1/2 is the square root of 1/12. We want the length to be 1, so multiply. This process is called the Gram-Schmidt orthonormalization process, and it is truly a sight to behold. That does raise the question, what is an orthonormal basis of C01? Recall that C01 is the continuous functions from 0, 1 to r. We have a little caveat. The word basis isn't going to work for us. We're going to need to stretch it. You see, for a basis, all the elements in a vector space can be written as a linear combination of the basis. But a linear combination, by definition, is finite. This is the correct interpretation of a basis. We're going to write vectors as infinite linear combinations. This might seem fine, but it raises convergence issues. For example, 1/1 minus x is equal to 1 plus x squared, and so on. But only if the absolute value of x is less than 1. This is the geometric series that you learn about in a second semester calculus course. If we just ignore convergence for the moment, then 1, x squared, and so on is a basis of C01. This is the Taylor series. In other words, every function can be represented as an infinite linear combination of these vectors. This is a terrible basis, though. We've already seen it isn't orthonormal. There are massive convergence issues. Just plug 2 into this equation. -1 is definitely not equal to 1 plus 2 plus 4, and so on. But worst of all, this will take a large number of terms to make the approximation be any good. An ideal basis should have two properties. First, it should be able to accurately approximate a large number of functions using a small number of terms. The fewer terms there are, the less memory it takes, and the faster the program will run. Second, the basis should be orthonormal. This makes it easy to find the coefficients. In a Taylor series, we can write f of x as a power series. The coefficients are then the nth derivative of f at 0 over n factorial. You might think derivatives are easy, and by hand, you're correct. But for a computer, derivatives are awful. A derivative requires you to divide by a small number, and computers don't like to do that. Another issue is that not all functions are differentiable. Compare this to an orthonormal basis. Then f of x can be written like this, so that the coefficients are an inner product, which is an integral. This probably frightens and confuses you. Integrals are hard. But for a computer, integrals are actually super fast and accurate. Now, why should you actually care about any of this? Well, all modern encoding is an application of this. This video was processed through an orthonormal basis. Some of the basis vectors are deemed not important, typically darker areas of the video, so those terms are dropped. The better the basis is at representing this video, the fewer number of coefficients they require. The smaller the file size of the video, the less bandwidth it takes to deliver the video, the cheaper it is for them to host the video. This is a very, very active area of math and computer science research. Even a basis that requires one fewer coordinates can save a company like YouTube millions and millions of dollars just in storage space. If you don't find that fascinating, I just don't know how to help you.